Hello everyone. Now we're starting chapter 8, conservation of energy. And this is not really a new topic that we're investigating. We're just going to look more details in this topic because we've been already using conservation of energy. This is how we set up chapter 7. It's usually the first equation that we use. And then in chapter 7, the focus was more on the work done and how it is related to the other energies, but now we are going to look at the bigger picture and with more details. So what we are adding is potential energy and internal energy in more detail. And there are a lot of problems in this chapter. Again, although chapter 8 is not really included in the exam coming up, and it will be on the next exam, but it is still very similar to chapter 7, so I think you're going to really benefit what we are talking today for the exam as well. Okay, so first thing, we are going to focus on potential energy. And so the potential energy is associated with the arrangement or the location of an object. And we are going to investigate two types, gravitational and elastic potential energy. So gravitational potential energy is related to the weight force, and elastic potential is related to the spring force. It's basically when they do work, that means there is also a potential energy or change in potential energy due to these. Okay, so we are gonna understand how to manipulate that in the energy conservation equation. And I've been already kind of showing a little bit of that in the problems that when I was solving. So hopefully now it's going to be more clear. So let's start with the gravitational potential energy. First of all, some forces like weight and spring force will be associated to the potential energy. Okay, and some you cannot associate it with potential energy. The difference between is related to whether the force is a conservative force or not. And I'm going to post another slide in terms of which forces are conservative and which ones are non-conservative. And again, weight force and spring force are the forces that are conservative. That's why you can associate a potential energy. So this is why we are doing it, but why they are conservative, I'm going to explain it in a different I have a video about it, and also I'm going to explain it later. Okay, I'll share the handouts as well. So for the gravitational potential energy, let me just highlight that. Okay, so again, it's about the weight force, and what the key thing is the elevation, as we've been emphasizing it. So at a higher elevation, an object has more potential to do something useful. So it will gain potential energy, and you can convert that energy to some other sorts of energy. So you can do something useful. We will use, since we are looking at the changes in energy in the energy conservation equation, we need to know which point is initial, which point is final. So we usually use like initial and final, kind of label them that way. Y is for the elevation. And when we apply the energy terms in the energy conservation, whether it is the work done by the weight force or the gravitational potential energy, this is very important. And I've been, again, talking about this before as well. Never include both of them, okay, in the energy conservation. You're going to choose one or the other. Last chapter was more about work, so most of the time we already calculated the work done by the weight force, so then let's just use that and then get rid of the potential energy. But now, since if they're not asking me to find the work done by the weight force, I'm probably going to ignore that in the work term, and instead I'm going to keep the gravitational potential energy on the left side in the energy conservation equation. Okay, so that's kind of what we do. And this is a tricky part for the energy conservation, but once you understand the reasons and have a couple practices, hopefully, again, it will help you to see the picture better, because we always start from the same equation and simplify. Next is the elastic potential energy, briefly. So this happens when you have a spring or an object acts like a spring, so you don't need a physical spring to have this energy. But if we have that in this case, so it's relaxed position, the spring is relaxed position, so that would mean this is x equal to 0, right, as we talked before about this. So that means there's no potential energy stored, because that depends on the stretch or compress. If there's none of those, then you don't have a elastic potential energy. And if we have a stretch, so we are stretching from here to there, so that will be some x which is non-zero, right, this point. That means we are, if you're holding it, stretching and holding it, that means we are giving the spring is giving the system some sort of energy, and that's called elastic potential energy. Another way of saying this is spring force is doing work, okay? But the key thing, you never include both of them in the energy conservation equation. You have to do one or the other, okay? So in the examples coming up, we are going to investigate those better, and hopefully it will be more clear. So let's just look at the kind of how we exchange the energy. So what we have here is we are throwing a ball upward, and we assume there's no drag, okay? And so let's just look at how the energy is changing. All the time you have to show where is the origin, kind of. So this is basically y is equal to 0, right? So we already have it here. I don't really need to write it here. And this is the initial case, so you kind of think about what you have. It really is helpful thinking about and writing things. This is the we're throwing it upward, y is equal to 0, velocity is v initial, because we're giving it an initial speed. But since I'm taking y to be 0, the potential energy, gravitational potential energy, goes to 0. And since there's velocity non-zero, kinetic stays, right? So kinetic is non-zero. And if I look at the final, when the ball is going upward, when it reaches the maximum height, that apex point, we know that velocity becomes 0. That will make kinetic 0, right? Because it's in the form of 1/2 mv squared. But since y is non-zero, then you will get the potential energy. So what we see is then from the bottom to top, for the upward motion, kinetic goes down and potential increases, right? And you can look at the changes, final minus initial. So in this case, this would be the initial case, and this would be the final for the upward motion. And you can take the differences. Kinetic would be changing kinetic would be negative, change in potential would be positive. So they are really the transfer is between the kinetic and potential, right? Initially you have kinetic, and then you're converting it to potential. At the top you only have potential, no more kinetic. In between those 2 points you have both of them, okay? But the total energy is the same, so energy is conserved, okay? And if you look at the downward motion, now the initial case is at the top, final is at the bottom, so it's going down. But we are still saying bottom is the 0y, as you can see. So the final potential will be 0 in this case. Again, and kinetic is going to be the same form. And you can see that these are the same values. They're both positive. So kinetic itself is always positive, because mass is always positive, v square always positive, so kinetic energy cannot be negative. But velocity is downward, right? It's going down, and here it was going up. So this downward velocity is negative because you're saying upward is positive. Just because velocity is negative doesn't mean kinetic will be negative, because kinetic doesn't care about the direction or the velocity. It cares about the speed, the magnitude, right? Keep that in mind as well. Energy is scalar quantity. And again, at the initial case, when the ball is coming down from the apex points, kinetic is 0. There's maximum potential energy. So in this case, kinetic energy is increasing because it goes from 0 to 1/2 mv squared, and potential is decreasing. And look at the signs. Now the kinetic is positive, right? And potential is negative. But it is, again, there is a transfer between kinetic and potential. Okay. So for the entire trip, and yeah, we do ignore the drag. For the entire trip, changing potential and changing kinetic will be 0. That kind of assumes that you start from the bottom and you end up at the bottom as well, right? So if you look at the two bottoms, then they have the same magnitude, so the changes will be 0. Okay. Later on we will also add drag and we'll see how that affects, but now we are making it still kind of simple and just focusing on the potential energy terms. So now if you consider a spring, stretched spring to a mass on a frictionless surface, later also we'll add friction too and we'll see how it changes. So instead of like throwing a ball upward, we can do similar thing with the spring, stretching, compressing, right? So that's what we are doing, and we are doing it on a horizontal case, so starting kind of easy. Later on, we will put the spring on an inclined surface, and we will see how to deal with that as well. And so the mass is pulled. This is the initial case here. You can see that the mass is pulled this way, right? And so there's a stretch, and then you just let it go. Maybe you're the one that applying that force, and I let it go. It's gonna start from rest. That would mean there's no kinetic energy because V is 0. And since this is the maximum stretch, potential is high. Okay, so those are the notes that we take. When the object is passing through the relaxed position, so this is in motion, we are just taking a snapshot and then looking at the object when it is coming towards the relaxed position. At that point, what happens? X is 0, that means there's no potential energy because there's no stretch or compress, but velocity is going to be actually maximum at that point. Okay, and that means it's high kinetic energy. And since it still has velocity, it's going to compress the spring. Okay, and this is the point that we are saying is fully compressed. That means it's gonna reach a 0 velocity. That would tell you there's no kinetic energy anymore, and you are compressing it that way. But again, since there's a compress or stretch, there's high potential energy, and the type of potential energy is elastic potential, not the gravitational potential. Okay, so there's no change in gravitational potential here, there's no change in elevation, but there's change in that stretch and compress. That means you will have a change in elastic potential. Okay, so now there are two types of potential that we need to understand and figure out if they're changing or not. Okay, so again, this is an example of showing how the energy is transferred between kinetic and potential, but this potential is the elastic one.